Hello, in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and a square. The radius of the small circle is equal to 1 unit. The side length of the square is equal to 3 units, and our mission is to find out the radius of this big circle. So first of all, we'll define the vertex of the triangle SA. We'll define this vertex as a B, and we'll define this vertex as C. We'll define the point of tendency of tangent BC with the small circle as D. We define the touching point of the square with the side BC as E. We define the point of tendency of the circle with the square as F. We define the point of tendency of tangent AC with the small circle as H. We define the point of the touching point of side AC and the square as I. We define the touching point of the square with side BC as J. We define the point of tendency of the square with the circle as K. We define the point of tendency of tangent AC with this big circle as L. We define the point of tendency of tangent BC with the big circle as Q. We define the center of the big circle as P, and we define the center of the small circle as O. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to 1. And we have here the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F, that is the point of tendency of tangent EI in this circle. Therefore, according to rule number 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency, then this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, according to the same rule, we have the radius OD that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius PQ that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. We also know that all the angles inside the square are right angles. So here, all the sides here are equal to 3 units. So here, this angle equals to this square, this angle will be equal to 90 degrees. The size of this angle is also will be equal to 90 degrees. This angle equals to 90 degrees. And finally, this angle will be also equal to 90 degrees. And here we have rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. Side BC is one side of triangle ABC, it is absolutely a straight line. So if you focus on the upper side of the straight line BC at point J, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of BC at point J to 180 degrees. This angle must be equal to 90 degrees. Exactly for the same reason, if we focus on the upper side of BC at point E, this angle equals to 90 degrees, therefore this angle will be equal to 90 degrees for the same reason. Okay. So actually, we found out that inside quadrilateral FOED, we have 1, 2, 3 right angles. Again, inside quadrilateral FOED, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay. So the sum of three angles is 270 degrees, and in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. Okay, so actually we found out that inside quadrilateral FOED we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral FOED as a rectangle. Why? Because it has 4 right angles. I write it down. Quadrilateral FOED, the small quadrilateral, is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, FO is equal to ED. FO equals to ED. Again, FO equals to ED. But FO is the radius of the circle that is equal to 1 unit. So I can write here FO equals to 1. And for this equation, 1 equals to FO equals to ED, we will derive that ED is also equals to 1 unit. Okay, here ED is equal to 1 unit. And right here the drawing that ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that OD equals to FE. OD equals to FE. Okay, OD equals to FE. But here we know that OD equals to 1 unit. So we can here, write here that OD equals to 1. And from this equation, 1 equals to OD equals to FE, we will derive that FE is also equals to 1 unit. can write down in the drawing that Fe equals to 1 unit. So if Fe equals to 1 unit and IE is one side of the square that is equal to 2 units, then IF will be equal to 3 minus 1, that is 2. Here IF will be equal to 2 units. Okay. So in the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. Actually, we can implement rule number 2 in our drawing, because in our drawing, if we focus on the common external point I, from the common external point I, we have two tangents to this circle, tangent IF and tangent IH. And according to rule number 2, they are equal to each other. That is to say, IF equals to IH. IF equals to IH, according to rule number 2. But here, IF equals to 2 units, therefore IH will be also equal to 2 units. Okay, IH equals to 2 units. Likewise, we'll focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CD and tangent CH. And according to rule number 2, they are equal to each other. That is to say, CD equals to CH. So if we define CH as X, then CD must be also equal to X because of the fact that they are equal to each other. So here we can write down that CH equals to X and CD also will be equal to X according to rule number 2. Okay, so in the next step, we'll focus on the right green triangle IEC. And we will implement the Pythagoras theorem on the right green triangle IEC. By PT is evaluation from Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is IC, therefore the square of the hypotenuse is IC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to IE square plus EC square. We'll repeat again, in the right green triangle IEC, according to the Pythagoras theorem, IC square equals to IE square plus EC square. So, what is the value of IC? It is very easy to see from the drawing that IC equals to 2 plus X. Okay, IC equals to 2 plus X, therefore IC square is equal to 2 plus X square. and it is equal to IE square. IE equals to 2 plus 1, that is 3. So therefore IE square is 3 squared, that is 9, plus EC square. What is the value of EC? EC equals to 1 plus x. Therefore EC square will be equal to 1 plus x square. So in conclusion, it found out that according to equation number 1, 2 plus x square equals to 9 plus x squared. Here we will open the brackets on both sides of equation number 1, and we will get that according to equation number 1, two plus x squared equals to 2 squared, that is 4, plus x squared plus 2 times 2x, that is 4x. And it is equal to 9 plus 1 plus x squared is 1 squared, that is 1, plus x squared plus 2x. So here we have, it is x squared. Here we have x squared on both sides of equation number 1, so x squared will get cancelled. What is left from equation number 1 after we cancel the x squared? In this side of the equation we have 4 plus 4x. In the other side of the equation we have 9 plus 1 is 10 plus 2x. Here we'll subtract 4 from this equation number 1, and we'll get that according to equation number 1, 4x equals to 10 minus 4 is 6 plus 2x. Here we subtract 2x from this equation number 1, and we get that 4x minus 2x is 2x. That is equal to 6. Here we will divide this equation number 1 by 2, and we'll get that x equals to 6 over 2 is 3. So x equals to 3 units. So here you can write down in the drawing that x equals to 3 units. And here also x equals to 3 units. Okay. In the next step, we join points O and H together by straight line. Point O is the center of the circle, point H is a point on the circle itself, therefore OH is the radius of the circle, that is equal to 1. R equals to 1. We have the radius OH that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. In the next step, we will join points C and O together by a straight line. And we will prove that those two wide green triangles can go into each other according to side rule. Okay, so I write it down. We will prove that the right triangle edge OC can go into the right green triangle ODC. So why those four right triangles can go into each other? First of all, edge O equals to OD. They are both the radii of the circle, therefore they are equal to each other. Edge O equals to OD equals to R, that is equal to 1. Okay, yeah, edge O equals to OD equals to R equals to 1. In addition, CH equals to CD equals to 3 units according to rule number 2. CH equals to CD equals to 3 according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side that belongs to both triangles. So, we actually proved that the two green small triangles can go into each other according to side rule. So I write it down. Triangle HOC can go into triangle ODC according to side rule. And from the fact that those two triangles can go into each other, we will derive that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define this angle as theta, then this angle must be also equal to theta. Why? Because of the fact that they are equal to each other. Okay. In the next step, we will join points edge and D together by a straight line. By joining points edge and D, we created here triangle edge DC. So, according to what we did until now, we can conclude that CO is the angle bisector of angle C. Why? Because it bisects angle C into two halves. Each half equals to theta. So I write it down. CO is the angle bisector of this angle, angle C. In triangle HDC. This triangle HDC. I repeat again. CO is the angle bisector of angle C in triangle HCC. Why? Because it bisects angle C into two halves. Each half equals to theta. Okay. In the next step, we will join points P and L together by a straight line. Point P is the center of the circle. Point L is the point of the circle itself. Therefore, PL is the radius of the big circle that is equal to capital R. In the next step, we join points C and P together by a straight line. By joining point C and P by a straight line, we created here two white big triangles. Triangle LPC and triangle PQC. Here we have the radius PL that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Actually, we prove that those two big right triangles can go into each other according to side, side, side also. We prove the triangle PLC, this big right triangle, can go into triangle PQC. So why those two triangles can go into each other? First of all, PL equals to PQ, they are both the radii of the circle, therefore they are equal to each other. PL equals to PQ equals to capital R. In addition, if you focus on the common start point C, from the common start point C, we have two tangents to the big circle, tangent CL and tangent CQ. And according to rule number 2, they are equal to each other. That is to say, CL equals to CQ. CL equals to CQ according to rule number 2. And finally, CP is a common side that belongs to all triangles, so CP equals to itself. CP equals to CP is a common side that belongs to both triangles. So we actually proved that the two big right triangles can go into each other according to side, side, side rule. So I write it down. The big triangle, triangle PLC, can go into the big triangle, triangle PQC, according to side, side, side rule. And from the fact that those two big right triangles can go into each other, we will derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two big right triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So here we will join points Q and L together by a straight line. By joining points Q and L, actually created here triangle LQC. So we can derive from what we did until now that PC is the angle bisector of angle C. I write it down. PC, or you can say also CP, doesn't matter. CP is the angle bisector of angle C. Why it bisects angle C into two arcs. Each arc equals to theta. In triangle LQC. In triangle LQC. I'll repeat again. CP is the angle bisector of angle C in triangle LQC. So we actually found out that angle C has two angle bisectors, CO and CP. They are both the angle bisector of the same angle, this angle C. Okay. In the next step, we will prove that CO passes through point P. Again, we will prove that CO, the angle bisector CO, passes through point P. So our claim is that the angle bisector CO passes through point P. I repeat again on our claim. Our claim is that the angle bisector CO passes through point P. Angle bisector CO passes through point P. We will prove our claim in a negative way. So in a negative way, we will assume that CO doesn't pass through point P. Repeat again on our assumption. According to our assumption, CO doesn't pass through point C. So, and the process of the proof will be that due to our assumption we will arrive to a contradiction, and therefore we conclude that our assumption is wrong. Therefore, our conclusion will be that CO indeed passes for point P. So this will be the process of the proof. Okay, so according to our assumption, if CO doesn't pass for point C, it means that we will have here two angles, angle OCD, angle OCD, this angle OCD equals to theta. This is the first angle that we have, angle OCD that is equal to theta. You can see from the drawing, it is very easy to see that CD is part of BC. Again, CD is part of CB. CD is part of CB. So if CD is part of CB, it means that CD and CB lie on the same straight line. Here, CD and CB lie on the same straight line. So CD and CB lie on the same straight line. Why? Because CD is part of CB. Okay. In the next step, I will draw angle PCB. Angle PCB. This is angle PCB. So this is angle PCB that I drew from the original drawing. So in these two angles, we have one angle that we can call it as a common. In these two angles, we have one leg that lie on the same straight line. That is to say, leg CD and leg BC, they are both lying on the same straight line. But what about the second leg? Leg CO and leg PC. Here we have the second leg of the two angles, that is leg CO and angle OCD, and leg CP in angle PCB. According to our assumption, CO doesn't pass through point P. So if CO doesn't pass through point P, it means that leg CO and leg CP are not lying on the same straight line. Okay? According to our assumption, leg CO, it is actually leg CO, and leg CP doesn't lie on the same straight line. Why? Because if CO doesn't pass from point P, it means that CO and CP doesn't lie on the same straight line. So we have here two angles. One leg of those two angles lie on the same straight line. That is to say, leg CD and leg BC of those two angles lie on the same straight line, while the second leg of those two angles, CO, doesn't lie on the same straight line as CP. And therefore, they can never be equal to each other, because one leg of those two angles lie on the same straight line, and the second leg doesn't lie on the same straight line. Therefore, they can never be equal to each other. Why? Because in order that those two angles will be equal to each other, if one leg lie on the same straight line, then the other leg must be also lying on the same straight line. Otherwise, they will not be equal to each other. And according to our assumption, the second leg doesn't lie on the same straight line. Therefore, they can never be equal to each other. So if this angle is theta, this angle will be equal to alpha, and alpha doesn't equal to theta. Alpha is not equal to theta. So we actually found out that angle C, this angle C, has two different angle bisectors. That is to say, CO and CP, that bisects it into two different halves, into two different halves. While angle bisector CO bisect angle C into two halves that are theta and theta, angle bisector CP bisects angle C into two halves alpha and alpha. And it is impossible. Why it is impossible? Because if angle C equals to 30 degrees, then any angle bisector will bisect it angle C into two halves, that is 15 degrees and 15 degrees only, and not to any other two halves. But here we found out that angle C has been bisected in two different halves, theta and theta and alpha and alpha. It is impossible. As you can see here, if angle C equals to 30 degrees, then any angle bisector will bisect angle C into two halves that are 15 degrees and 15 degrees, and not any other halves. So due to the contradiction, we will conclude that our assumption that CO doesn't pass for point P is incorrect, and therefore CO indeed passes for point P. Okay? Here, CO passes for point P. So we finished with the proof. In the next step, we'll focus on the right green triangle, triangle ODC. On the right green triangle, triangle ODC, this angle equals to theta, this angle equals to 90 degrees, therefore the third missing angle must be equal to 90 degrees minus theta. 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle, and especially in triangle ODC. Likewise, we'll focus on the big right triangle, triangle PCQ. On the big right triangle, triangle PCQ, this angle equals to 90 degrees. This angle equals to theta, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. Okay? So in the next step, we'll prove that triangle PQC, the big right triangle, is similar to the small right triangle, triangle ODC. we will prove that the big right triangle PQC this big triangle is similar to the small green right triangle ODC. So why those two triangles are similar to each other? First of all, we just right now found out that those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. Angle QPC, this angle is equal to this angle, that is actually angle COD. Repeat again. Angle QPC equals to angle COD. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So we can find out that angle PQC in the big right triangle is equal to this angle, that is actually angle ODC. Repeat again, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta, is a common angle that belongs to both angles, so angle theta equals to itself. Or we can define angle theta as angle PCQ. And it equals to itself, so we can define angle theta as angle OCD. Repeat again. So this question states that angle theta equals to itself. It's a common angle that belongs to both triangles. So actually we proved that the big triangle PQC is similar to the small green triangle ODC according to angle similarity rule. So I write it down. The big right triangle PQC is similar to the small right triangle ODC according to angle similarity rule. And for the fact that those two big right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PQ, the big right triangle, over OD in the small right triangle is equal to QC in the big right triangle over DC in the small main right triangle. I repeat again. We conclude that PQ over OD equals to QC over DC. Okay. So PQ equals to R, it is the radius of the big circle, over OD. OD is the radius of the small circle, that is equal to 1. And it is equal to QC. What is the value of QC? It is very easy to see from the drawing that QC equals to 3 plus 1 plus 3, that is 7, plus QJ. So QC equals to 7 plus QJ. So I substitute QC by 7 plus QJ over DC. What is the value of DC? Here DC equals to X, that is equal to 3 units. So I substitute DC by 3. So in conclusion, I found out that according to equation number 1, R equals to 7 plus QJ over 3. Here we'll multiply this equation number 1 by 3, and we'll get that according to equation number 1, R equals to 7 plus QJ. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, QJ equals to 3R minus 7. And we found out that QJ equals to 3R minus 7, so we write down in the drawing here that QJ equals to 3R minus 7. QJ equals to 3R minus 7. Here, because of the fact that the side length of square KIJE is equal to 3 units, we will examine 3 possibilities for the value of the radius of the big circle. The radius of the big circle would be less than 3 units. This will be the first case that we examine. The value of the radius of the big circle will be equal exactly to 3 units. This will be the second case. And finally, the radius of this big circle could be greater than 3 units. This will be case number 3. So we check each case in order to find out which case is relevant to our drawing. Okay. So already mentioned here, we'll examine the second case. If R is less than 3 units. This is case Number 1, that R is less than 3 units. So if R is less than 3 units, then we will have a circle with a radius that is less than 3 units. So I will draw the circle. This is the radius. And because of the fact that the side depth of the square is equal to 3 units, then it will be higher than the radius. So this will be the side depth of the square. We have the radius here that is 1 to the point of tendency, therefore this angle will be equal to 90 degrees. So here in quadrangle PLQJ, we have 1, 2, 3 right angles. So here, therefore the fourth angle must be also equal to 90 degrees. Therefore, inside quadrangle PLQJ, we have 4 right angles. Therefore, we relate to quadrangle PLQJ as a rectangle. Quadrangle PLQJ is a rectangle because it has 4 right angles. note that the opposite sides of a rectangle are equal to each other. That is to say, PL is equal to QJ. PL equals to QJ. But according to our assumption, PL equals to J. PL equals to R. PL equals to R. And for this equation, R equals to PL equals to QJ. We will derive that R equals to QJ. R equals to QJ. And R equals to QJ. So QJ for one side it is equal to R. From the other side it is equal to 3R minus 7. So for this equation, R equals to QJ equals to 3R minus 7, we will derive that R equals to 3R minus 7. Here we subtract R from this equation and we get that R minus R is 0, 3R minus R is 2R minus 7 equals to 0. So here we will add 7 to this equation and we will get that 2R equals to 7. Here we will divide this equation by 2 and we will get that according to this equation R equals to 7 over 2, that is 3.5 units. So here we arrive to a contradiction. Why? Because according to our assumption, R is less than 3 units. So R cannot be simultaneously less than 3 units and also equal to 3.5 units. So due to the contradiction, we conclude that R cannot be less than 3 units. Okay. So we'll examine the second case, that R is equal to 3 units. Case 2 is that R equals to 3 units. So if R equals to 3 units, we will draw a circle that equal exactly to the radius of the circle is equal exactly to 3 units. Okay. Here R equals to 3 units. And the side square of the square is also equals to 3 units. And the radius of and the side square, they are both with the same height. So here the radius is drawn to the point of tendency, therefore this angle equals to 90 degrees. So inside quadrilateral PKQJ we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral PKQJ is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. This is to say, PK is equal to QJ. PK equals to QJ, but here, know that PK is the radius of the circle that is equal to 3 units. So we can write here that PK equals to 3. So for one side, here, so from this equation 3 equals to PK equals to QJ, we will derive that QJ is equals to 3 units. QJ equals to 3 units. So from one side QJ equals to 3 units. From the other side we have already found out that QJ equals to 3R minus 7. And from this equation 3 equals to QJ equals to 3R minus 7. We will derive that 3 equals to 3R minus 7. So here we will add 7 to this equation and we will get that according to this equation 3 plus 7 is 10, so 10 equals to 3R. We divide this equation by 3 and we get that R, the radius of the big circle, is equal to 3 and a third. But according to our assumption, R equals to 3. R cannot be simultaneously equals to 3 and a third, so we got a contradiction, and due to the contradiction, we cancel the possibility that R equals to 3 units. So we're left only with the third possibility that R is greater than 3 units. So if R is greater than 3 units, so we will draw a circle with a radius that is greater than 3 units. Therefore, the radius will be higher than the side length of the square that is equal to 3 units. You can see here the radius is higher than the side length of the square. Okay. So here, from point K, we draw perpendicular on the radius PQ. Repeat again, from point K, we draw perpendicular on the radius PQ. So here, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. So inside quadrata, so we'll define the touching point of the perpendicular from point K and PQ as T. So inside quadrilateral TKQJ, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral TKQJ is a left angle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say Kj equals to Tq. Kj, yeah. Kj equals to Tq. Kj equals to Tq. But here Kj equals to 3 units, it is the side of the square. That is equal to 3 units. And for this equation 3 equals to Kj equals to Tq, we derive that Tq is also equals to 3 units. Tq equals to 3 units. So what is the value of Pt? From the drawing, it is very easy to see that the value of Pt is equal to PQ minus TQ. Again, PQ minus TQ equals to Pt. I write it down. Pt equals to PQ minus TQ. That is to say, Pt equals to PQ, that is R, the radius of the big circle, minus TQ, that is 3. So in conclusion, we found out that Pt equals to R minus 3. Likewise, according to the sum that the opposite sides of a rectangle are equal to each other, we get that Tk equals to Qj. Tk equals to Qj. But we already found out that Qj equals to 3r minus 7. So we can write here that Qj equals to 3r minus 7. And from this equation Tk equals to Qj equals to 3r minus 7, we will derive that Tk is also equals to 3r minus 7. In the next step, we'll join points P and K together by a straight line. So here, point P is the center of the circle, point K is the point of the circle itself, therefore Pk is the radius of this circle that is equal to R, or capital R. So in the next step, we'll implement the Pythagoras theorem on the right triangle PTK. So I'll copy the right green triangle in a new page and we'll implement the Pythagoras theorem on right triangle PTK. Okay. So this is actually the right triangle PTK that they copied from the original drawing. So we implement the Pythagoras theorem on this right triangle PTK. So you write it by PT, that is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the apertures equals to the sum of the squares of the perpendiculars. So the hypotenuse is pk, therefore the square of the hypotenuse is pk squared. That is equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to pt squared plus tk squared. So according to the Pythagoras theorem, pk squared equals to pt squared plus tk squared. So here pt equals to r, therefore pk equals to r, therefore pk squared equals to r squared. That is equal to pt squared. Pt equals to r minus 3, therefore pt squared equals to r minus 3 squared. Plus tk squared. Tk equals to 3r minus 7, therefore tk squared will be equal to 3r minus 7 squared. So here we will open the brackets on this side of equation number 1, and we get that according to equation number 1, r squared equals to r minus 3 squared. R minus 3 squared equals to r squared plus 3 squared, that is 9, minus 2 times r times 3 is minus 6r, plus 3r squared is 9, 3r minus 7 squared is 3r squared, that is 9r squared, plus 7 squared, that is 49, minus 2 times 3r is minus 6r, and minus 6r times 7 is minus 42r. So here we have r squared on both sides of equation number 1, so r squared will get cancelled. What is left from equation number 1 after we cancelled r squared? In this side of the equation nothing is left, so we have 0, that is equal to 9r squared minus 6r minus 42r is minus 48r. 9 plus 49 is 58, so it's plus 58. So we have here a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58. And here the variable that we are looking for is r, so x equals to r. So we put the data inside the formula for x, and we find out the value of the values of r, because x equals to r. And we get that according to the formula for x, we get that r equals to minus b. Here b equals to minus 48, therefore minus b is minus 48, that is plus 48, plus minus square root of b squared. B is equal to minus 48, therefore b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 36, times c. C is 58, so minus 36 times 58 is minus 2088 over 2a. A is 9, so 2a is 18. So here we'll get that R equals to 48 plus minus square root of 2304 minus 2088 is 216. So we left the root only is 216 over 18. So here we have R equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here the radius in the big circle R, we have two possibilities for the value of R. The first possibility is that R equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031 over 18. And 33.3031 over 18 is 1.85. So we found out that according to the first solution, the radius of the big circle R equals to 1.85. But because of the fact that R cannot be less than 3 units and 1.85 is less than 3 units, we cancel this solution. So we left only in the second solution that R, the radius of the big circle, equals to 48 plus 14.6969 over 18. 48 plus 14.6969 equals to 62.6969 over 18 is equal to 3.483 units. So we found out that the radius of this big circle, capital R, equals to 3.483 units. Okay, here R equals to 3.483 units. We finished to answer the question. In the next step, I'll summarize the lecture. Okay, so in the drawing we have a big triangle. Inside the big triangle we have two circles and the square. The radius of the small circle is equal to 1 unit, and the side length of the square is equal to 3 units. And our mission is to find out the radius of this big circle. So in order to answer the question, I presented to you 3 rules, and we use the 3 rules during the proof and during the answer on the question. So, according to rule number 1, A tangent to a circle is perpendicular to the radius drawn to its point of tendency. We have here tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Why? Because whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. It's rule number 1. Then I presented to you rule number 2. That the lengths of two tangents from a common external point to a circle are equal. So we have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. And finally, we use the third rule in this to answer this question. According to the third rule, the sum of the angles on one side of a straight line is equal to 180 degrees. CD is a straight line, so if you focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees. So which angles we have on the upper side of CD at point O? We have angle alpha and angle beta. Therefore, the sum of those two angles is alpha plus beta. It must be equal to 180 degrees. Okay, so by using those three rules, we arrive here to the conclusion that for the radian OFED is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, FO equals to ED. FO equals to ED. But we know that FO equals to 1, it is the radius of the circle. So from this equation 1 equals to FO equals to ED, we will derive that ED is also equals to 1 unit. ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that FE equals to OD. FE equals to OD, but here OD equals to 1 unit. It is the radius of the circle. And for this equation, 1 equals to OD equals to FE, we will derive that FE is also equals to 1 unit. FE equals to 1 unit, therefore quadrangle FOED is not a rectangle but a square. And we also know that all the angles inside the square are right angles. And here we used actually rule number 3 in order to get the value of this angle. BC is a straight line. So the sum of the angles on the upper side of BC at point J must be equal to 180 degrees. If this angle equals to 90 degrees, this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of BC at point J to 180 degrees. This angle must be equal to 90 degrees. Likewise, for the reason exactly, this angle must be also equal to 90 degrees. If you focus on the upper side of BC at point E, this angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees. Okay, then we used here rule number 2. If we focus on the common external point I, from the common external point I, we have two tangents to this circle, tangent IF and tangent IH. And according to rule number 2, IF equals to IH. But here, what is the value of IF? IF is 3 minus 1, that is 2. So if IF equals to 2, then IH must be also equal to 2 because of the fact that they are equal to each other according to rule number 2. Likewise, we focused on the common external point C. From the common external point C, we have two tangents to this circle, tangent CD and tangent CH. and according to rule number 2, they're equal to each other. That is to say, CH equals to CD. But here, so if we define CH as X, then CD must be also equal to X because of the fact that they are equal to each other. Then we implemented the Pythagoras theorem on this right green triangle, triangle IEF. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, IC squared equals to IE squared plus EC squared. The right triangle, triangle IEC, according to the Pythagoras theorem, IC squared equals to IE squared plus EC squared. IC, what is the value of IC? IC equals to 2 plus X. Therefore, IC squared equals to 2 plus X squared. And it is equal to IE equals to 3, therefore IE squared is 3 squared, that is 9, plus EC squared. EC equals to 1 plus X, therefore EC squared equals to 1 plus X squared. So in total, we found out that 2 plus X squared equals to 9 plus 1 plus X squared. We open the brackets on both sides of this equation, equation number 1, we found out that 2 plus X squared equals to 2 squared, that is 4, plus X squared, plus 2 times 2x, that is 4x, and it is equal to 1 plus x squared, it is equal to 1 plus x squared equals to 1 squared, it is 1 plus x squared plus 2x, and we have also here 9. Okay, so here we have x squared on both sides of the equation, so x squared will get cancelled, but is left from equation number 1 after we cancel x squared. What is left is, in this side of the equation we have left with 4 plus 4x, that is equal to 9 plus 1, that is 10, plus 2x. We will subtract the 4 from this equation, equation number 1, we found out that 4x equals to 10 minus 4 is 6 plus 2x. So 4x equals to 6 plus 2x. We subtracted 2x from this equation, equation number 1, and found out that 4x minus 2x is 2x. That is equal to 6. We divided this equation, equation number 1 by 2, and we got that x equals to 6 over 2, that is 3. So here x equals to 3 and x equals to 3. Then we join points O and H together by a straight line. OH is the radius of the circle, and this angle equals 90 degrees according to rule number 1. Then we prove that those two very small triangles can point to each other according to side rule. Why? Because we have here edge O equals to OD, the above the radius of the circle, therefore they are equal to each other. Likewise, and we also have CH that is equal to CD according to rule number 2, and they are both equal to 3 units. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. So we actually found out that those two green small right triangles can go into each other according to side rule. And from the fact that the triangles can go into each other, we derive that those two angles are equal to each other. According to the rule, the corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two angles must be also equal to each other. So if one angle is theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay, so we joined points and edge and D together, edge and D together by a straight line. And we created here triangle HDC. So we can conclude from what we did until now that CO is the angle bisector of angle C. Why? Because it bisects angle C into two halves. Each half equals to theta. So CO is the angle bisector of angle C in triangle HDC. Here CO is the angle bisector of angle C in triangle HDC. Then we join points P and L together by a straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the big circle that is equal to capital R. Then we joined point C and P together by a straight line, and we created those two right green triangles. This angle equals to 90 degrees according to rule number 1. So we proved that those two right big triangles can point to each other according to side rule. Why those two triangles can go into each other? First of all, PL equals to PQ, they are both the radii of the circle, therefore they are equal to each other. In addition, we have, if we focus on the common start point C, from the common start point C, we have two tangents to the circle, tangent CL and tangent CQ. And according to rule number 2, they are equal to each other. That is to say, CL equals to CQ. And finally, CO is a common side, CP is a common side that belongs to both triangles, so we actually proved that those two big right triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles can go in triangles are equal to each other. Those two triangles can go into each other, therefore those two angles must be equal to each other. So if one angle is theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So then we join points L and Q together by straight line and we create a triangle LQC. So we can conclude until what we did we can conclude that here that PC is the angle bisector of angle C, because it bisects angle C into two halves, each half equals to theta, in triangle LQC. Yeah. CP is the angle bisector of angle C in triangle LPC. So angle C is two angle bisectors, CO and CP. Then we had the claim that CO passes for point P. CO passes for point P. Here, the angle bisector CO passes for point P. We proved this claim in a negative way. We assumed that CO doesn't pass for point P. By this assumption, we arrived to a contradiction. Therefore, due to the contradiction, we concluded that our assumption is incorrect, and therefore, CO, we must conclude that CO must pass for point P. This is the process of the proof. So we have the assumption that CO doesn't pass for point P. So if CO doesn't pass for point P, then we have here two angles, angle OCD that is equal to theta. This angle OCD equals to theta, and you can see here that CD passes, CD is part of P. CD is part of CB. CD is part of CB, therefore they are both lying on the same straight line. Okay, here CD and CB lie on the same straight line, why? Because CD is part of CB. Okay, then we have the second angle that I drew, angle PCB, angle PCB. This is angle PCB. Okay, so we know that the first leg on those two angles are DC and BC, and they're both lying on the same straight line. So the proved. What about the second leg of those two angles? We have leg OC and leg PC. According to our assumption, CO doesn't pass for point P. So if CO doesn't pass for point P, it means that CO and CP are not lying on the same straight line. Because if they are lying on the same straight line, CO must pass for point P. But according to our assumption, CO doesn't pass for point C. Therefore, CO and CP are not lying on the same straight line. Okay, CO and CP doesn't lie on the same straight line. So we have here two angles. One leg of those two angles lie on the same straight line, while the other leg of those two angles are not lying on the same straight line. Therefore, those two angles can never be equal to each other, because in order that those two angles will be equal to each other, if the first leg lie on the same straight line, then the second leg must be also lying on the same straight line. But according to our assumption, the second leg doesn't lie on the same straight line, therefore those angles are two different angles. If this angle is theta, this angle is alpha. And theta is not equal to alpha. So we actually found out that angle C is two different angle bisectors that are CO and CP, and bisected into two different R's. While the angle bisector CO bisects angle C into two R's that are theta and theta, the angle bisector CP bisects angle C into two different R's that are alpha and alpha. And it is impossible. Why? Because if angle C equals to 30 degrees, any angle bisector of this angle C will bisect it into two 15 degrees and 15 degrees only, and not to any other arms. And here we found out that angle bisector that C will be bisected into two different arms. Okay? And so here, due to the contradiction, we must conclude that our assumption is incorrect assumption. Due to the contradiction, we conclude that our assumption is incorrect, and therefore CO indeed passes for point P. CO passes for point P. Then we focused on this right triangle ODC. In the right triangle ODC, this angle equals to theta, this angle equals to 90 degrees, therefore the whole triangle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big triangle PQC, big right triangle, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we prove that those two right triangles are similar to each other according to angle similarity rule. I'll explain what I mean. Here, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta is a common angle that belongs to both triangles, so this angle equals to itself. So we actually found out that those two triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we conclude that PQ over OD equals to QC over DC. Again, PQ over OD equals to QC over DC. PQ equals to R, OD equals to 1, it is the radius of the small circle. What is the value of QC? QC equals to 3 plus 1 plus 3 to the 7 plus QJ. So we substituted QC by 7 plus QJ, and DC equals to 3. So we substitute DC by 3 and found out that R equals to 7 plus QJ over 3. We multiply this equation by 3 and we found out that 3R equals to 7 plus QJ. We subtracted 7 from this equation and we found out that QJ equals to 3R minus 7. So we can write here that QJ equals to 3R minus 7. Then we examined, because of the fact that the sine length of the square is 3 units, that we examined 3 possibilities for the value of R. R can be less than 3 units, R can be equal to 3 units exactly, and R can be greater than 3 units. So according to the first case that R is less than 3 units, we have this drawing. You can see here that the square is higher than the radius because it is equal to 3 units and R is less than 3 units. So here this angle equals to 90 degrees according to rule number 1. So inside quadrangle P, L, J, Q we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees, therefore quadrangle PLQT is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, PL equals to QJ. Okay, PL equals to QJ, but PL is R, so PL equals to R. So from this equation, R equals to PL equals to QJ, we will derive that R equals to QJ. Okay, R, that QJ equals to R. QJ equals to R. So from one side, QJ equals to R. From the other side, QJ equals to 3R minus 7. And from this equation, R equals to QJ equals to 3R minus 7, we derive that R equals to 3R minus 7. We subtracted R from this equation and found out that R minus R is 0 and 3R minus R is 2R. So in conclusion, found out that 0 equals to 2R minus 7. We added 7 to this equation and found out that 2R equals to 7. Here we divided this equation by 2 and found out that R equals to 7 over 2, that is 3.5. R equals to 3.5 units. While according to our assumption, R is less than 3 units. R cannot simultaneously be equal to 3.5 units and also less than 3 units. So due to the contradiction, we cancel this possibility, that is to say R cannot be less than 3 units, and we examined the second possibility that R equals to 3 units. So if R equals to 3 units, we will have this drawing. Again, this angle equals to 90 degrees according to rule number 1. So in quadrangle PKQC, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, therefore quadrangle PKQG is a rectangle, because it has 4 right angles, and you know that the opposite sides of a rectangle are equal to each other. That is to say, PK is equal to QJ. But here PK equals to 3, so we can write here that PK equals to 3, and from this equation 3 equals to PK equals to QJ, we will derive that QJ is equal to 3. So from one side QJ equals to 3, from the other side QJ equals to 3R minus 7, so from this equation 3 equals to QJ equals to 3R minus 7, we derive that 3 equals to 3R minus 7. Here we added 7 to this equation and found out that 3 plus 7 is 10, so 10 equals to 3R. We divided this equation by 3 and found out that R equals to 3 and a third. But according to our assumption, R equals to 3. R cannot simultaneously be equal to 3 and a third, so due to the contradiction, we cancel this possibility. R cannot be equal to 3 units. And then there we have the last possibility that R is greater than 3 units. If R is greater than 3 units, then we will have this drawing. You can see here that the radius is higher than the square. Here from point J we draw perpendicular on the radius PQ, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So in quadrangle TKQJ we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrangle KTQJ is a rectangle and the opposite sides of a rectangle are equal to each other. That is to say KJ equals to TQ, but KJ equals to 3 units. Therefore from this equation 3 equals to KJ equals to TQ, we will derive that TQ equals to 3 units. Then we have according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that TK equals to QJ. TK equals to, here what is the value of PT? PT equals to PQ minus TQ. PQ minus TQ, so PT equals to PQ, that is R, minus TQ, that is 3. So in conclusion, found out that PT equals to R minus 3. Then, according to the sum rule that the opposite sides of rectangle are equal to each other, we get that TK equals to QJ. But QJ equals to 3R minus 7. So from this equation, TK equals to QJ equals to 3R minus 7, we derive that TK is also equals to 3R minus 7. Then I copied the right green triangle PKT in a new page and implemented the Pythagoras theorem on this right green triangle PKT. This is the right triangle PKT that I copied from the original drawing. According to the Pythagoras theorem, PK square equals to PT square plus TK square. PK square is R square, PT square is R minus 3 square, TK square is 3R minus 7 square. So we solved this equation. We have quadratic equation. We solved this quadratic equation, and we got here two answers. We have the first answer to this quadratic equation is that R equals to 1.85 units, but R cannot be less than 3 units, and 1.85 is less than 3 units, so we cancel this solution, and we have the second solution that R equals to 3.483 units, and here R is greater than 3 units, so according to our analysis, this is a possibility that we don't have any contradiction if R is greater than 3 units. So the answer to this question is that the radius of this big circle is equal to 3.483 units. Okay, repeat again. The radius of this big circle is equal to 3.483 units. Okay, thank you very much.